you know.
I mean, yeah.
I mean, like during the test, I'd be like, I thought I understood the material.
That would be actually something here.
Dang, that is tough.
Oh my God.
Honestly.
Well, you know, it's like,
Pretty
I
reasonable
mean,
reaction.
that's somebody that's really expecting punishment, right? Because they sit there for 90 minutes and took a calc test that was
Yeah.
a semester ahead of what.
And trying to figure it out.
Yeah.
I'm here now.
I mean, props to them though. They really were like, you know, yeah, I guess it's hard. So I'm just trying to figure it out.
So this is what we were going over. X modulo of the ideal driven by F, where f of X is minimal polynomial, and K of X such that zero. And when I say minimal, I mean with respect to degree. Number C, the degree of KU over K is equal to N, the degree of F, in the notation above, and B, every element of KU is uniquely or can be written uniquely in the form sum I equals 0 to n minus 1 of ki. Okay, so last time we were chit-chatting about this. We got this, and we got this as a byproduct. If we proved this one right here. And then we got that since KU is contained in KU, and this must be the quotient field of this, and we got that this KU was a field, and so there we go. So we took care of that. The degree of KU over K, so let's continue to prove. Last time we got where F generates I, which was the set of G KX, that's the G of U equals 0. We convinced ourselves last time that this I was in fact a prime ideal. Then we noticed the KX is a PID, so it's a maximal ideal. And it's a non-zero ideal because of the fact that U is algebraic. Note f of x divides g of x for all g of x such that g of u is 0. So f is minimal. So it's the smallest degree polynomial since g of u equals 0 because it divides every other polynomial that kills u. So this kind of completes this. We also get that k of u equals this because of the fact that k of u is a field, and it's in fact a quotient field of this. This must be a field because this quotient, this is a PID or modulo of maximal ideal, so it's a field. So that's k in round brackets u. So this thing now, I claim that the degree of the vector space KU, synonymously K square bracket U, is of degree F, right? The degree of KU over K is equal to this end. So let me prove this. Right. F of X, n minus 1 with AI and K. Let me point out that there's no loss in generality of me writing f of x as a monic polynomial, because I'm assuming that the degree of f of x is n. So that means that the coefficient of the x to the n term is not 0. And since it's not 0, I can just divide out. Am I okay with this? So to get this, I claim that the set 1 u squared all the way up to un minus 1 is a basis for a right, okay. That alpha KU, which is isomorphic AX mod F, okay. So I claim first set 1 u squared up to un minus 1 spans KU. Well, note that KU is equal to the image of F. Let's see, where P goes from KX KU via P H of X HP. Right. In fact, last time that's when we got this isomorphism, we had this thing, which was in fact a actually a surjection of rings, and we modded out by the kernel. Right. So note any of is of the form K0 plus K1 X plus to K, L, X, L. Everybody okay with it? Or KI. So what I've done is I've written a typical coset down. I claim that we can assume that L is no more than n minus one, where n is the degree of f. Any ideas on how to do that?
You say it again.
My claim is, so here, this is an arbitrarily large polynomial, right? So an element of kx might have arbitrarily large polynomial plus the ideal generated by f. This is a big fat coset. I claim that I may not have chosen this representative very well, and I can choose it actually with L is no more than the degree of that last term is no more than n minus. Right. You basically, right, you run the Euclidean algorithm on this. Right. So notice that. This is equal to Q of X. With R equals 0, well, R of X is 0, or degree of R of X less than n. So yes. Because KX is PID.
So it's a Euclidean.
Oh, I'm sorry. Yeah, you're right, calling out that KX is PID, yes, but in fact, it's Euclidean domain. Right, division, when you have polynomials over field, the division algorithm works with the degree function.
I remember.
Right.
Yes.
So that means that R of X equals K0 plus K1X plus KLXL plus F of X, Q of X, and I guess that really should be minus, shouldn't it? And this is actually in the ideal generated by F. So in other words, I can replace this part with R of X of degree and more than that. So, so any element of index in your written K0 plus K1X minus 1, K minus 1 plus this. And this is at U level, the isomorphism associates so in other words, the set of elements 1 U squared, U minus 1 span. Because everything here, the set of powers of X cosets span this, and X's are associated with U's by this original phi. So there you go. So now we've got its spanning set. How do we know it's linearly independent? So we know that this is a spanning set, so the degree is less than or equal to n. But maybe this is too much, right? Maybe it's a linearly dependent set and I could have made it smaller, but you can't. Okay? And the reason is independent. Well, let me pick something else. AI and K such that A0 plus A1U, A minus 1, N minus 1, 0. You guys see what the problem with that is? That looks an awful lot like a polynomial, right? That's a polynomial equation that U is a root of, right? What is the degree of this? It's less than n, right? For sure. So, but minimal polynomial for U is degree n. And this looks like degree less than n, so my only choice is above must be 0 polynomial. That is AI equals 0 for all I. Therefore, this truly is a basis. Everybody okay with that? And let me explain, the last statement basically says every element of KU can be written uniquely as a linear combination of powers of UI. That is exactly because the powers of UI form a basis, right? Remember, a representation by basis is unique. Everybody cool with that? So that gives you the last bit. Okay, any questions on that? Let me give you kind of a fun example here. There, in this chapter, there's, I think, a lot of fun examples. Consider wait a minute. Let's capture a moment. By the way, what do you know about the roots of this? So in particular, one of the roots is the fifth root 2, right? So that is correct. There are 4 other roots, and they appear in complex conjugate pairs. Now, if you have any of these roots, what Z and U be any two of these roots, right? I mean, everybody agrees that there's actually 5 of them in the complex numbers. And actually, this is a solvable polynomial, so you can actually write down what I've written down one of them, and actually it's not terrible to write down all of them. By this theorem, take the smallest field that contains Q and one of these two roots, C. This is isomorphic to QX on but notice this takes no notice to which root I use. Now, this is kind of interesting because you've got one real root and then you've got these two pairs of complex conjugates. Let's suppose that U is the real root. This is isomorphic to the smallest field that contains Q and 2 radical 5. It's of degree 5 over Q. It's got a basis 1, 2 to 1/5, 2 to 2/5, 2 to 3/5, 2 to 4/5. That's a basis for it. This is isomorphic to the field you obtain when you stick on one of the complex roots, right? And by the way, when you stick on that complex, one of the complex roots Z, that field will not contain its complex conjugate. Yeah. And so this one has basis 1, Z squared, Z cubed, and Z to the 4th. And the powers of that, none of the powers of that, except for the 5th power and the 0th power, are in fact real. This is interesting to me because notice that this field right here is totally real. That is, it's a subfield of real numbers. This field, if Z and U are different, is not a subfield of real numbers, and yet they are isomorphic, which is kind of maybe a little bit surprising. Yeah, so QU, if U is the real one, is a subfield of the real numbers. QZ is a subfield of the complex numbers, but it's not a subfield of real numbers. Okay, any questions? Okay. Theorem. So let's talk about these extensions. Suppose I have a homomorphism, an isomorphism of fields. By the way, I'm assuming K and L are fields here. By the way, I guess really the only adjective here, if I wanted to be super, as general as I wanted to make my statement, instead of writing isomorphism, I could just say an epimorphism of fields. Why is that all I need here? I claim that if that function from K to L is an epimorphism of fields, it's also an isomorphism. This is kind of a silly point, but I think it's worth remembering. Every homomorphism from a field to a field is always one-to-one. Somebody explain why that's true. Nothing so fancy, really. How do you check if something's one-to-one? say something, I'm sure there'll be a kernel of truth to it. That is correct. That's how you check if something's one-to-one. You look at its kernel, right? Suppose your domain is a field. What do you know about the kernel? It's an ideal of K. How many ideals of a field are there? Only the zero ideal, right? So if you have a function whose domain is K, it has to be one-to-one, or it has to be the zero homomorphism, which I'm not allowing with the ring identity, right? So really, these things you always expect to be one-to-one, but this, all you need here is on to make the statement. I'm not going to be so mysterious, but this is an isomorphism of fields. Comma, U, an element of an extension field K. And V, an element of an extension of L. Then we can extend that homomorphism to an isomorphism. Under, we need some conditions here. I'll just look at taking U to V. If and only if one of the following holds. One silly case is, can anybody name a case when for sure you can do this? Condition on U and V. Okay, so one condition is U and V are transcendental, right? Over and L. Number two, U is a root. U is a root of f of x, a of x, and V is a root of tornado of x. And let me make clear what I mean here, just in case there's any confusion. If f of x is a0 plus a1x, xm, then when I apply a little tornado to it, it just, oops. And notice that those coefficients are in L, right? So it's just what, so this is a homomorphism that takes K's to L's, and it's just what this thing naturally does to the polynomial. There. Okay. Proof. Let's see what this is true. Let me make the first quick observation that this can be in any case. I can extend this to this bigger map from KX. Where X is in fact what you think it is. It's an indeterminate. So I can extend this to an isomorphism of rational functions where so this is what I mean by extended. It means when you restrict it down to the original domain, here K, you get the same thing. So in particular, the way this extension works is the way I think it would work. This is the sum of tornado AI, XI. Okay, so if one holds, that is U and V are transcendental, then just compose the following isomorphisms. We know that KU is isomorphic to KX. So just compose these three isomorphisms, and you get KU is isomorphic to LD. And this preserves K as well. What about a two holds? Then consider the following. Consider KU this is an isomorphism. I should put a bar over this. What I mean by putting the bar over this is right. What I mean here is this is basically, remember, this thing is defined on rational functions. I can restrict this down to just polynomials. And here, what we have is the image of this. Well, that is anything in the ideal generated by F is in this image here. So this gives you a well-defined homomorphism right here, which is isomorphic to L. Okay. And again, just like in this example, it's worth noting here. Yeah. Are roots of Fx. I'm assuming that F is reducible. If you don't make this assumption, this is not true, and it's easy to make contradictions here, then A is U is isomorphic. And in fact, this is beginning the seeds of Galois theory, because what this says is, if I walk up to you on the street and give you an irreducible polynomial of degree 15, then you've got 15 roots, complex roots, say it's a polynomial over Q. And any pair of those roots give you isomorphic fields, even though these fields actually may be different. They may actually be different fields, they are isomorphic. So here's another example along this ilk. Of this ilk, as you say, example. Let alpha be the real cube root 2, and this is called primitive third root of unity. This is, of course, a complex, not real number. If you cube this, this is actually e to the I2 power 3. So if you cube it, you get 1. Notice that this satisfies this, and more particularly, it's the root of this polynomial. In fact, this is a factor you take. If you multiply this by omega minus 1, you get omega cube minus 1. This is a primitive third root of unity. The fields Q, third, Q, to the 1/3 omega, and Q to the 1/3 omega bar, which, by the way, in this case, omega bar, the complex conjugate of omega, is the same thing as omega squared, are distinct. Notice, for example, it's clear that these two are different because this one contains complex numbers that are not real. And this one's totally real. It's a subfield of the real numbers. And these two actually, notice that 2 to the 1/3 is not in either one of these, as a matter of fact. These are distinct fields, but are isomorphic. Because these are the 3 roots of that polynomial. 3 roots of x cubed minus 2, which is an irreducible polynomial over Q. So there are your 3 roots. So those things make 3 distinct but isomorphic fields. It's also interesting to note that the intersection of these 3 fields is the rational numbers, right? The only stuff that's in all 3 of these together are just the rational numbers. Okay, any questions on that? Okay, here's another important theorem that kind of builds us up to where we're headed here. let K be a field and F a polynomial degree. Then there is a simple extension of K so this F is obtained by taking taking K and sticking some other element of an extension field on it, such as the following hold. Number one, there exists U and F such that F of U is equal to 0. The degree of this extension field is no more than n, and you get equality holds if and only if. Anybody will guess the condition you need for equality here? Condition maybe on F. Little f. So the degree of extension is less than or equal to n, and equality on that extension is n if and only if f is irreducible. And if f is irreducible in kx, this is irreducible, then ku is unique up to ki isomorphous. Right. Look back at this example really quickly here. You can join three roots of this. When I say unique, I don't mean there's only one. I mean there's only one up to isomorphism. These three fields right here in the previous example are three fields that are different, but they're unique up to K isomorphism. Ku is often called the field obtained by adjoining U to K. So let's go through, see how far we can get into this rabbit hole. Okay, the first thing I'm going to do is I'm going to start off by factoring f of x over k of x. So let's factor in to say some m factors. Where pi x m x. And we'll see. So assume that those the factors that I broke them up into is irreducible. And of course, this means the degree is greater than or equal to 1. 3 zeros are units, in fact. We now have KX mod the ideal PIX in the field for all between 1 and m, because KX is a PID. And irreducible polynomials generate maximal ideals in KX. So let me make an observation here. I now claim that, in fact, these are all fields, and I claim that K is a subfield of this. The composition is 1 to 1. Of course, this part is not 1 to 1, but the no, I got that wrong. Yeah. But the composition is 1 to 1. So if you got a K, it follows you to K, and so K is a subfield. Identified with or PI for each one of these, eyes. So my claimed root of this is we'll find our claimed root U from part 1. Consider the projection pi from KX where pi of x, well, given by goes, where do you think it's not a projection that goes on to just goes to its coset. Notice that pi of PIX is the 0 element. Let me write that out for. So pi of PIX is 0 element. And so U is our claim root. So that's enough for today, but so what do we have? There's a U and F such that F of U is 0. Well, what we found is we found this U such that PI is equal to 0. And so, and if it's a root of one of the factors of F, it's certainly a root of F. Okay. Any questions on it? Any questions out there? Okay, well, y'all have a good one. Let me also almost start plugging the AWM, I think it is going to do a Pi Day thing on March 14th, Pi Day, from 5 to 7. There's gonna be like pizza and fun and games and that sort of thing. So I encourage y'all to mark your calendars for that, and I will see you all next time.